So, good day and welcome everybody to yet another lecture of our AAMP series. And today I'm going to talk about magnetic resonance in principle. Fortunately, we have already some extension videos from last year, which help a lot, especially the first one, which makes the link to knowledge from previous lectures, mainly experimental physics, electrodynamics. So I don't have to go into these details. That will save me some time. And I think today the overall lecture will be therefore a little bit shorter, but let's see how this goes. Okay, so first thing to do is I'm going to share my screen with you. Swap to the slides. And get going. Can you see the slide 46, high resolution spectroscopy?
Yes.
Okay, thank you very much. All right, so, okay, today we switch into a different type of technology that's used for spectroscopy. We're speaking of high frequency spectroscopy, which is actually a term stemming from the electric engineering point of view, because if you compare this to the frequencies that we've been working with in infrared spectroscopy or in electronic excitation in the UV and visible range, this would be in a terahertz regime, and now we're actually in a much lower frequency regime between megahertz and gigahertz. But from the electric engineering point of view, this is considered high frequencies. And it's an interesting type of physics, because now our electromagnetic waves have wavelength in a macroscopic range, right? So they are actually something that you can really see in terms of extension in your lab, for example, by looking at those devices which are used to transfer power from a sender to a receiver. In this frequency regime, so from a gigahertz and up, it is more efficient to use so-called waveguides to transfer this power. And in German, you say Hohlleiter, so you can see one example here. And if you look at the Hohlleiter, they are typically formed in this rectangular shape, made of metal, and are adjusted to the frequency range that you are interested in. Basically, the longer side of the rectangle that you can see here is half of the wavelength of the largest wavelength that basically fits into this resonator, and is therefore a lower limit for the frequency that can be transmitted through this waveguide. Now, what are we using these waveguides for? We're going to use them. You will see them in the typical lab setups that work in a in this regime where we are either dealing with spin processes of electrons or spin processes of nuclei. So we are in a regime of, for example, hyperfine interaction, if we are looking at nuclear flips, or we do electron spin resonance spectroscopy, or ESR, also called EPR, but I'll get to this later in this talk today. So direct adsorption is the first way of how we can measure the resonance of our piece of matter that we're interested in. So we have a sender that creates a certain electromagnetic field with a given frequency, and we use these waveguides to bring this power into the adsorption cell, where part of this energy is adsorbed if we are in resonance with the frequency of the sender. And on the other side, we have a receiver where we can measure the amount of adsorbed energy. That would be a direct adsorption measurement. So I'll check sweeping through the frequency and look where I have my resonance, because if I'm in resonance, with my sample, I'm depositing energy in my sample and therefore have a reduced signal at the receiver. So that is the first way of doing it, the direct adsorption measurement. Now, second type and more effective is to do an adsorption in a magnetic field. Why? Because the magnetic field will give us another handle on bringing the whole system into resonance. Because if we have a system and the system has a magnetic moment, then the magnetic dipole has a certain energy in the magnetic field, depending on its direction with respect to the field direction. So by changing now the strength of the field, so by varying the B field, for example, I will change the point of resonance for this excitation in this piece of metal. And so the first thing I can try is I can keep a given frequency fixed, for example, with which I'm doing the excitation from one level to another level. And I'm tuning through the magnetic field. And that means that I'm basically changing the relative position of the energy states in my system. And at some point, I will reach a distance in this energy space, basically a distance which is in resonance to the electromagnetic field that I'm offering. And therefore, I have a resonance achieved. And I can see this if I look at intensity of adsorption as a function of the magnetic field. I can also turn this around and keep the B field constant and go through the frequency range, right? So then I have a certain splitting, which is given by the fact of the absolute value of my B field. And I'm changing the frequencies by tuning through my field generating device. And at some point, I will be in resonance and therefore have an increased adsorption of my electromagnetic field in my probe. So these are the two scanning methods. And now we come to the detection of our resonance. So the direct adsorption measurement would be simply to measure what's left of the original signal. And obviously, if I'm in resonance, I have an attenuation, a reduction of my signal in my receiver. Type B is called the Purcell's method. It's on this slide shown in the lower left picture. So we have a magnetic field, and we have our sample in this homogeneous constant magnetic field, here illustrated through north and south pole. And I bring in a coupling coil and have a sender. Now, what I'm measuring is I'm not measuring the strength of a signal in a receiver, but instead I'm measuring the attenuation of the sender. So there is a certain damping of the sender in the moment when the system is in resonance with my internal transition in the sample. So this is a method where I'm directly feeling, right now, my radiation that I'm generating in the sender is accepted by the sample, and I have a higher energy consumption in the coil at resonance. This is the Purcell's method. And in comparison is given option C, Bloch's method. Here we are measuring the discrete flips of the magnetic moment caused by induction. Okay, so here, if you look at the lower right side of slide 47, you can see a similar setup. We have the two poles, north and south. This gives us our constant and approximately homogeneous field with the field lines in X direction. And then you can see a coupling coil, which is perpendicular to this, and an induction coil, which is arranged with its X parallel to the static magnetic field. And so with the coupling coil, since it's perpendicular to NS, I can induce a flip, a change of the direction of the magnetic moment, so of the spin of the atoms in this sample. And when this happens, let's think about a flip, for example, of a magnetic moment pointing upwards, now pointing into the direction of NS. You'll see I'll change basically my B field, and therefore have a change over time. I'm inducing voltage into the induction coil. I can measure a current, and this signal can be used to detect the resonance in the sample when I'm going, for example, through frequencies offered in the coupling coil. So these are the detection methods: direct, Purcell, which measures the attenuation, or Bloch's method, which directly measures the activity of flipping a spin. Now, before going into details, one thing in the extension video, I'm making for you this link to knowledge on magnetic moment created by a rotating charge. So it's a video takes about 15 minutes, and it will remind you how this is explained. If you think of, for example, a charged particle in a circular fashion, you have a charge rotating. You can say that the magnetic moment from electrodynamics is the product of the current and the area of this little coil. And so you can relate this to the frequency of this rotating charge and come up with a connection between the angular momentum of this caused by this rotational motion of the charge and the magnetic moment that is generated. Okay, so if we have a charged particle which has this has a spin or angular momentum to it, then we have this creation of a magnetic moment. And if you take a magnetic moment and you put it into a magnetic field, then you would see what? So you take a dipole, a magnetic dipole, and you put it into a magnetic field. What would the dipole do?
So classically, maybe try to align itself, but like a rotor start to how do you call this motion of this the precision or
Yes, but why? The precision is something that comes in because of a different aspect. If it was just a magnetic dipole itself,
okay, it would try to align itself.
It would try to align itself, and if there was friction, it would have this oscillation and come to a point where it is then perfectly aligned to be in the minimum energy position, right? So here, in this case, first of all, we don't have a friction. So there will always be something acting. And what is it actually that acts on a dipole in a homogeneous field? It's not a force, but it's
moment.
Yes. In German, we say Moment. Here, this is a false friend. It's better to speak of a torque. So Drehmoment is torque in English. So there's a torque acting, and it will lead to the alignment of the dipole basically to the field. Now we have a different situation. If it was without friction, we would have this kind of never-ending oscillation. But it is not just a dipole in this homogeneous field. It is a dipole linked to another constraint quantity of the system. What is conserved? What else does this system that we have, the rotating particle, which property does it have? Which actually gives rise to this phenomenon of a magnetic dipole moment. It is a charge rotating, therefore it is something that has an angular momentum. And now we are in the situation that we have something with an angular momentum. We can write it as L in a field which causes a torque on this particle. And this is something we can connect to this setup, for example, in experimental physics 1, the gyroscope, where you have a spin. And this spin is placed in some field, into our gravitational field, and therefore there's a torque acting. And what happens, you already indicated it in your answer, a spin, if a torque is acting on it, will do what? So this spin or a top, it's actually called a top, so an Kreisel, yeah, is showing which type of movement. If there is a torque acting on the top, a precession, exactly, a precession movement, because if you think about it, if this is our system and we have something rotating here, then the angular momentum will be in the direction of my finger. If you then have force acting like this, pointing downwards, then you have a torque which is perpendicular to the 2 and is therefore perpendicular also to L, and will only change L in its direction, but not in its actual length of the vector. So therefore L, the angular momentum, will change over time, so but only in its direction, not in its length. So the vector will start to rotate, and this is what we call the precession motion that we see in this case. And exactly this is what's happening here in the case of having a magnetic dipole attached to a spinning particle that has an angular momentum in this magnetic field. And
what's the force here that is orthogonal to the actual angular momentum? The magnetic force from the outer field, or?
Yes. So it's the same. You can think of it like in the electrostatic picture. You would say you have an E field and you would have an electric dipole. The electric dipole is something that's easier to think of because you have a negative and a positive charge, which is the source and the end of the field lines. But on these two charges, you will have force acting, one in this direction, one in this direction. So you have two forces in opposite directions at a certain distance from the center of mass, and therefore you have this moment of torque. In the mechanical situation, you can think of it in a very similar way by saying that the flux of the magnetic field on each of the poles is the equivalent to a charge in space, only for the fact, or except for the fact that there are no magnetic charges, obviously, so there are no magnetic monopoles, and somewhere the field has to go also into the source. So when you have a pole, the north pole, where the field lines go out of, then inside of the magnet you have an incoming component of the field, because there are no magnetic monopoles. But you can think of this area as something like a source of field lines, if you just think about field lines out of the magnet. And then the picture is basically the same. There's one force acting on this pole here and one force on the other one, causing the torque. So this is what causes the torque here in our top, in our Kreisel, and causes this precession movement. Now, in this extra slide, or in this extra video, I'll explain to you that the prefactor that connects the angular momentum, L, to the actual magnetic moment, which is typically written as mu. And I also explained to you why the actual precession frequency that you obtain is, if you convert this into an energy, the energy for the flip of a, for example, spin down to a spin up in this external field. Okay, so just look it up. It takes 15 minutes, and then I think everything should be clear. Now, back to our slides here. Before we go into details of NMR, here a quick reminder of on what's going on if a single atom is brought in a magnetic field, just for you to remember the quantum numbers that we introduced. For example, we have a state which is described as a doublet pi 3/2. What does this tell you if it's a doublet pi 3/2? which quantum numbers can you derive from this abbreviation of the state?
Is the 3/2 the total angular momentum?
Exactly, it's the total angular momentum of the electron hull. This is typically written as J, and J is built from which coupling? If it's the total angular momentum of the electron hull,
Yeah, the spin-orbit coupling.
the spin and the orbital angular momentum, right? So it's L and S. Now, what does this 2, I said it's a doublet P 3/2. What does this 2 mean? Written as a superscript before P.
Doubly degenerated, or?
Yes, doubly degenerated if there is no field that splits it, because it's actually referring to the spin multiplicity, right? So if it's 2, means there are 2 possible ways of how the spin can be arranged. So it must be an S of 1/2, a single electron. And then what is this P telling us?
The orbital?
Yes, the orbital angular momentum. And what's the size of the orbital angular momentum here?
2. That 1.
1, exactly. Yeah. So L is 1, so it's a P state. And now we see in this case, we are looking at a situation where L and S are aligned to give a total angular momentum of the electron hull of 1 plus 1/2, giving us 3/2. And this is indicated as the subscript after the P. So it's the 3/2 version of the P if we have a single electron with spin 1/2. And now what we do is we bring this system into a magnetic field. So now all of a sudden one direction can be distinguished from the others, and we have a splitting of the formerly degenerate orientational quantum numbers. You can see here. Oh, I'm too fast. I'm too fast, sorry. I skipped one step, namely this step here, where we introduce yet another quantum number, which is termed F. What could F be? So here we said L and S combine to J, and then there is something else written here. It says I equal 3/2. What is I?
Maybe
The spin of the nucleus.
Exactly, yeah. So this is the nuclear spin is 3/2, and so F is then what?
The superfine structure. So now we again combine this
Exactly, yeah, the
electron hull J with this new
right
momentum.
Exactly. So it's the hyperfine structure. We're combining J with I to get F. It's okay, super would have worked as well. It's the same message, right? So it is a structure that is beyond the fine structure. It's the hyperfine structure because we have now also interaction with the nucleus if the nucleus has a spin. And so what we obtain is F. So if you look now at the F, the possible combinations of F that you can reach at by combining, it's obvious from the fact that J is 3/2 and I is 3/2. So there can be a minimum F of 0 and a maximum F of 3, right? By combining to get minimum and maximum values. So F goes from 0 to 3, giving us 4 possible ways of how these two angular momenta can be aligned. And then we put this now into a magnetic field. So you can see what's coming up. If you go into a magnetic field, then each of the F components splits into its formerly degenerate MF levels, right? Because if we don't have a magnetic field, it doesn't matter how F is oriented with respect to our laboratory axis. But the moment we introduce a magnetic field, the orientation becomes relevant. And if we look at the algebra for angular momenta, this Lie algebra, you see there are 2J plus 1 possible orientations or projections that our F can have onto this reference axis introduced by the magnetic field. And so for F equals 3, this gives us 2 times 3 plus 1 possible ways of how it's oriented, right? So this gives us 7. And for F equal 2, it gives us 5. For F equal 1, it gives us 3, and so on, right? So if you look at the splittings and you count them, it's in total 16 levels that we have now in the magnetic field if our field is not too strong. So then we are in the Zeeman range. What is going on if I move from here to here? What's your guess? What's happening here in this regime?
Maybe we start to make this when it's just an idea that we say we take, for example, the total F2. And if we increase the magnetic field, we increase the spacing between these two states. So maybe they start overlapping with the free states from above.
Right. So you could stay in this picture and use the MF quantum number to refer to the states all the way through any tuning of your magnetic field. You could stay with this quantum number MF, but it's no longer a good quantum number, as spectroscopists say, because it doesn't really relate to an energetic ordering anymore. Because if the field is too strong or stronger than something else, namely the coupling between J and I, it makes more sense to classify the states with respect to a different set of quantum numbers, a different set of orientational quantum numbers, namely the magnetic quantum numbers of J and I. Okay, so you can think of it this way, that if the field is stronger than the interaction between A and J, then you will basically have a splitting of the larger magnetic dipole in this field, which is the J component, so the electric or the magnetic dipole created through the electron hull. This gives us 4 big portions because we go from J equal 3/2 to minus 3/2. So we have 3/2, 1/2, minus 1/2, and minus 3/2. This is the splitting due to the orientations of the electronic magnetic dipole. And for each of these orientations of the magnetic dipole moment, you have a subspacing with respect to how the nuclear dipole is oriented in the field. And for each of them, for each of the MJs, you have the 4 possible MIs, giving you 4 times 4, again 16. So you can see that it's basically just a convenient swap or switching to a different set of quantum numbers to have a description that is better fitting the actual ordering with respect to energy. From the mathematical point of view, you can use any basis to describe your states, but it's better to classify them in something that makes more sense in terms of how they are grouped energetically. And you can think of it this way. You can say in a perturbational approach to the situation you have without the field, it depends on how which of these terms comes in terms of strength, in terms of order in this perturbational approximation, right? So you can say, okay, I'm taking spin-orbit coupling as the first component, and then comes the field, or I'm doing the field interaction first, and in this basis, I'm expressing then my correction due to spin-orbit coupling. So this is simply 2 ways of working with the same problem, and your coupling matrix will look different depending on which basis you work with. But if you diagonalize it, you get the same energies. It's just that in one case, your quantum number, for example, the MF quantum number in a high field situation doesn't really help you anymore with respect to the energetic ordering of the states, right? So you would switch to this combination of MJ and MI. Okay, so this is just to warm up. This is the hyperfine splitting in a atomic system, a doublet pi3 half state, if the nucleus has also a spin I equals 3 half. All right, now the experimental setup. How does such a nuclear magnetic resonance machine typically look like? You can see it on the right-hand side of this slide 49. It is basically a huge Dewar type vessel because you would like to cool this down. You need very, very strong magnetic fields for this type of experiment. And in order to be able to create these high currents in this electromagnet that you built, you have to cool this so that you're in a superconducting regime for the material that you're using. Otherwise, you would have way too much loss through heat, and it would be absolutely inefficient and not really, and you wouldn't be able to realize this type of setup with such a high B field that you need. Now, my question for you is, why do we actually need these high B fields now? What are we going to measure? We are going to measure a hyperfine structure of a magnetic interaction. So the hyperfine or the Zeeman effect, if you can think of it, a Zeeman effect in the hyperfine structure. Yes, please.
Maybe the resonance distances are proportional to our magnetic field, and as the hyperfine structure has an initially so small scaling, so a small magnetic moment, we need high magnetic fields to get the energy distance in an applicable range for our radiation that we put in.
You're on the right way, but you cannot change the size of the dipole moment of the object that you want to flip, right? But you're right, the energy, you said
the energy.
Yeah, so the energy, because we know the energy is direct proportional to the B field. If you think about the energy, first think of the torque of a dipole in a homogeneous field. It's the dipole as it's defined as length d or as length mu in the magnetic field times the actual field, the E field or the B field. So that would be the torque. Actually, it's the vector product. So it's mu cross B giving you the torque. But if you integrate over the angle, and since the angle is dimensionless, torque and energy have basically, in principle, same units. So you have an energy which is the scalar product of mu and B. Right? So if you increase B, meaning you have a stronger magnet, you have more current going through your coils, then you will have a larger energy splitting, or the energy difference that stems from a different orientation of your spin is larger. And you would like to get to this point because what we are going to quantify is a adsorption, meaning that you would like to have the states as far away as possible in terms of energy distance, because if they are close to each other, they will have almost the same population. Because if you look at how energy levels are populated, you have to look at the Boltzmann energy distribution, and obviously if the energy difference is very, very small, then the population of both levels will be almost the same. And there won't be any transition that you can detect, right? So you would like to have a significant difference in population between the levels, and this gets better and better the further these two levels are apart. So this is shown in this equation here, where you just take the relative for the number of states in level 2 over the number of states in level 1, and this is directly related to E to the minus and then the energy difference between these states over K Boltzmann times temperature. And this is unfortunately approximately 1 for the energy ranges that we are dealing here, where we have energy differences, as I said, in the range of gigahertz. So here we have to really try to get our B field as large as possible. And how are we going to change now population? We're going to use this high field strength, and we will do it in a pulsed excitation. If you have a continuous excitation of a two-level system, we know already that this doesn't really help, or the best that you can get is actually which situation? So two-level system, continuous excitation. What's going to happen? What is your equilibrium state of population in this case?
50-50.
50-50, exactly. And why? Because the Einstein coefficients for adsorption from 1 to 2 and for induced emission from 2 to 1 are the same, if they are not degenerate in the upper and lower level. So you want, it's happening the same time that you have an excitation from 1 to 2, as you see a de-excitation from 2 to 1. So in a continuous radiation, you would get in a two-level system, you would only get a 50-50 population. So it will be the same in both levels. But still, this is different from the thermal distribution, because obviously in the Boltzmann distribution, the lower state will be slightly higher populated than the excited state, right? So this is something you can also measure, hopefully, if your B field is strong enough. Okay.
May I ask a question?
Yes, sure. Mm-hmm.
To which temperature do I have to cool down the
Well,
measurement?
the cooler, the better. But this is so. This has to do with the actual setup of how you create the magnetic field, which is through electric magnets, and so you have to be at least under the temperature for superconduction in this type of material that you're using, because this is what's basically limiting your ability to create such a strong magnetic field. So you have to be below this temperature where you jump into the superconducting state.
I would have a question.
Mm-hmm.
The levels which are close in energy, and you said that they are almost equally populated, and therefore you need the high magnetic field. But doesn't the change in the temperature because of the Boltzmann distribution also give the same population difference? Because if you cool down more, if the temperature is lower, then the N2 to N1 gets bigger too, isn't it?
Yes, exactly. So it's another effect that helps. As you can see in this equation, you have E to the minus and then the energy difference over K Boltzmann and temperature, right? And so you want this term to be as large as possible, this term in the exponent. So you want to have a very big change in energies E2 and E1, and also low temperature, because then in the best case scenario you will have almost all the atoms in this ground state. So you're right. So obviously also the low temperature helps you with this, but it's mostly the B field that is then technically used, because here you can gain a lot of splitting just by creating higher B fields in the range of it depends, but up to 20 Tesla is an option today. Okay.
Pulse excitation, we would space it then that we always have the time that the excited states fall down again. Is this the general idea into the pulsing, or?
So yeah, if you do a pulsing, you can in principle also go into states where you are not in an equilibrium. So this can also be used as an advantage because then you also have a simple an enforced population difference. Like think of the laser where you have population inversion through another lever coming in where you have a certain delay and you can pump. So if this is also possible, then this is another way of creating more intensity in your signal, right? So pumping is another alternative to, or it's another thing that helps you with the problem of equivalent or very similar populations in your levers. And this is now the first type of relaxation that we will be looking at, the so-called longitudinal or spin lattice relaxation time. And you might ask yourself, why is it called longitudinal relaxation time? What is longitudinal here? And the idea is the following. So if you have your magnetic dipole moment in a field, we said it's not going to stay like this. It's not steady because we have the situation of a top in a field where a torque is acting, and therefore it is doing this precession motion. Okay, so all our magnetic dipoles are circulating on some cone. And if you look at what's constant, you see that only the projection of this mu onto the axis of your field is constant in time. And this is called the longitudinal magnetization of your sample that you have. And in this type of relaxation that we're looking here, which is called the longitudinal relaxation time, we're just looking at the time it takes for the magnetization to change its sign, right? To go from -1 to +1, for example. So we're talking about the longitudinal component, with longitudinal meaning the projection of the magnetization onto the field axis. Okay, so that's why it's called longitudinal, and it is a relaxation that happens due to couplings of the spins to the environment, to the lattice they're sitting in, right? So the atoms are in some solid matter arranged in a symmetric fashion, and the spins are not separate in the sense of separate and completely untouched degrees of freedom that the system had, and so there will be some thermalization happening, and this means that they will find ways to relax back down to the minimum energy situation, which is in our case the alignment of the mu with the field direction of the external magnetic field. So if we have at some time, let's assume we did a continuous wave, we have reached a situation where both states, the excited state and the ground state, are equally populated. So it's the same number of processing dipoles in this direction and in this direction. It's a 50-50. And now we wait some time, and we wait till the population goes basically back to this thermal equilibrium state, where the lower state has the higher population according to the Boltzmann distribution, right? So this is what we call the relaxation time. So we look at how long does it take until this occupation of the E2 state is reduced to 1/8 of it. So this would be our typical T1 time, the relaxation time for the longitudinal component of the total magnetization of your probe to go back to the state of minimum energy. What's the mechanism again? The coupling of the spins to their environment, opening a channel for thermalization. This is the time T1. The other time that we're interested in is the so-called transversal or spin-spin relaxation time. And this is a decay constant for the transversal part of your magnetization. So if you do an excitation and you do it in a coherent fashion, then this means that all of your cones or all these vectors which rotate on these cones due to the precession have a phase-locked motion, right? They're all in the same phase to each other. And this means that if you look at the projection of the magnetization onto the XY axis, it is rotating. Okay, so you have a certain signal. You can think of it as a signal of, for example, if you put a coil along the x-axis and you have something rotating, this mu now rotating in this xy plane, then you have a signal that you can measure in the coil along the x-axis, right? And so this is what comes into play due to this coherent excitation, but also this situation of having them all in phase is not for eternity, but also has a certain relaxation where you have a distribution of your vectorial positions in time over the whole cone, right? Does this
It's
sort
a
of
bit too fast for my thing, so I was lost halfway through your explanation.
okay? Yeah, look at this situation here. For a certain time t, we have the magnetic dipole here illustrated as a vector rotating. We have this precession movement along the axis. In our case here, it's along the z direction. And you can see these are different atoms, but they all have the same phase-locked situation here, right? So they all, if you look on top, from top down, they all these vectors are on top of each other, right? And at some time t plus t2, this phase-locked situation is gone, and they have a random distribution with respect to each other. There is no phase relation. So on average, there is no longer any component of your magnetization that is changing over time in the xy plane.
But this left-hand case is really something specific. Naturally, they do not need to lay on top of each other. They have to just be in a certain fixed phase relation to each other.
Now the idea is that you really align them so that they have the fixed lock, so a locked position, all at the same, if you look on top, all at the same position in projection. Yeah.
How do we come to this thing?
Yes.
So
yes.
why do we come to this conclusion this would be the case?
How to get there, right? So this is something that I'll show you on the next slide, because the idea is that you do this with a so-called p-half flip. You do a pulse, you do a pulsed excitation. Let me see if this is coming here. Okay, this. Let me go straight to this in a first explanation. What you do is you introduce a magnetic field along the x direction, meaning you have a coil which has its axis along the x direction, and then you switch on here for a certain time so that you have a magnetic field coming in that does now exactly what's happening in the actual static homogeneous field along the z-axis. It causes the magnetic dipole to make a precession motion. But if the field is now along the x direction, you have a precession from the z-axis, for example, towards the y-axis. Okay? If you give it a pulse excitation with a length that stops exactly after 90 degrees turn. And now, after this turn, you have conserved a certain amount of magnetization with a preference direction along where you flipped it to, so along this in this XYZ, and then this will be your situation in this time after. So you have flipped the spin in this XY direction, and now the spin is rotating in this XY plane because of the still persisting static B field in the Z direction. So you have prepared it in a state where you have a clear non-equilibrium distribution in the XY plane because of this flipping. But this will also be lost over time because of some other process, this so-called transversal relaxation time. The spins each other between the spins of the atoms, they are also coupled. There's a spin-spin interaction, and there is the possibility to also dissipate energy, and therefore you also lose this prepared state of a defined magnetization in the XY plane. It is rotating. It gives you the signal in the coil attached to the Y, also this Y axis. Yeah? If it turns like this is where your Y axis is standing. You have the coil here, and because of this rotation, you get a signal. But you have, because of this transversal relaxation process, the magnetization vector getting smaller and smaller, because it's eventually in an equilibrium where all of the cone positions are again possible at the same time, and your netto or your net magnetization in this plane will be zero. And the time for this to happen is the time T2, the transversal relaxation time. So transversal and longitudinal is just the magnetization component. So is it longitudinal, then along the Z axis, and if it's transversal, then it's perpendicular to your field axis. And you have two different mechanisms that are here involved. In the longitudinal, it was this coupling of the spins to the lattice and giving away to lattice vibration and other effects. So this is where you're coupling, and here it's a coupling directly between the spins that are rotating. Okay, now how are we going to measure this? Since it is a relaxation time, and it is some finite time it takes for this coherence in the transversal case to be lost, you will see a certain broadening in frequency space. Right? So in the frequency domain, if you look at intensity as a function of frequency, you will have a peak with a certain width. And from this peak width, you can, in principle, determine this times T1 and T2. So this would help. This would be one way to measure T1 and T2. And these two numbers can be linked to, for example, the types of spins and spin environments that you can find in this piece of matter. So it will help you to identify which type of matter this is, right? So this is the actual idea in nuclear magnetic resonance spectroscopy, that we can learn about what is it that we have in our sample and where is it. So I'll get to this later, but this is in the medical sciences was a revolution to have this kind of high resolution in terms also of which type of matter or tissue is somewhere in space, right? If you scan over a person or whatever, then you can distinguish basically between different types of tissue because of different environments for the spins doing this precession, but we will get there. So first, T1 and T2, these are our criteria, or this is what we use to identify types of matter. I said we can measure this in frequency space, but it's often better to do it in a time domain through Fourier spectroscopy, where you work with pulsed excitations. And I'm going to, this is a slide I kept, this from a previous lecture. What it just does, it is talking about two-level systems, like we were just discussing in the case of having a spin flip from this position to this position. We can think of it as a two-level system, and we have an external perturbation through some electromagnetic wave that comes in, and then you can set up the Schrödinger equation for for this system and do perturbational theory in order to describe what's happening if there is an external field coming in that is modulated with a certain frequency because it is an incoming electromagnetic wave. And the thing that you can see is that your solution for the wave function of this two-level system is something that is a linear combination of your two solutions for the upper and the lower state with prefactors that are a function of time. I mean, makes sense. There's something going on. It's a little bit lower state than the upper state and lower state again. But if you look at how this varies in time, you can see it has the coefficients themselves vary as trigonometric functions, cosine and sine, of omega t. And this omega, which appears in the argument of your trigonometric function that does the oscillation, is proportional to two things. One of them is basically the field strength of the incoming perturbation or electromagnetic wave, and the other thing is a coupling operator between the two electronic states and dependent on which type of states it is, right? So, but the only thing to see is that obviously, if this is the wave function, then the squared absolute value of this gives us the probability of finding the system in one of these two states. And so if you look at the population of the lower state with respect to the population of the upper state, you see that this has a cosine on sine squared omega t variation. And so this means, okay, if I can, in the time domain, now choose my excitation length, yeah, so the time I'm exposing the system to this perturbation, if I adjust it accordingly, I can exactly adjust the population. If I go for a pi pulse, in terms of angle, it is omega, right? If I go for a pi pulse, then I'm reaching a total inversion. I'm getting from the, if it was in the ground state, I would get everything in the excited state and the other way around. And for a pi half pulse, I'm exactly in between. And this is now better explained in a different picture, in this picture of a rotating dipole moment, which gives rise to this energy level, upper and lower level. We said for the lower level, it will be a mu rotating this way. And for the upper level, it will be a mu rotating this way. And so it is rotating because we have a B field, which is along the Z axis, we said, right? And because of the precession movement. And my perturbation that does now the flip is a B field that comes in perpendicular to our static field. And now all of a sudden I have a B field in this direction. So the mu will also show a precession movement in with respect to the field lines in this, for example, X direction, okay? Because this is how I came in with my coil. The coil is then, can you see what I'm doing in terms of on the screen? Because this is important. Yeah, okay, thank you. So right, so this is the X-axis. This is how the coil is set up so that we have the B field coming like towards you right now. And so the dipole moment, which was precessing like this in the static field, will also now, while doing this motion, make a precession in my created X field, right? So it will be moved if I'm giving it just a pi half pulse from this position into this position. And see what we've done? We have flipped the magnetization from the Z direction into the X direction. And why is there a remaining magnetization now in X direction? Well, we said if in the static magnetic field without any excitation, if this is our precession movement, then the time average is just a projection onto this axis, right? Because everything else, the other components, they're compensating. So the time average would be a magnetization into the Z direction for the excited, for one of the states, right? So, and if I I can also think of it as an ensemble average, because if there is no coherent relation between the precessing spins in the magnetic field, then all positions on the cone are present at the same time. And the net magnetization is only what remains in this Z direction. And now comes my excitation with the B field along the x-axis. And all of a sudden, boom, I flip them all into the xy plane. And now this time constant component of M is lying in the x direction and is now still doing the precession movement, because we still have the B field in Z direction acting. But at the moment I'm flipping it in this direction, if I have placed a coil here in the Y direction, coiled like this, every time the magnetization passes my coil, I'll get a signal. Okay, so by the flipping, I get a signal coupled into my coil, which measures exactly the precession frequency. Okay, so that's what's happening. And now back to what we are actually interested in. We said we're setting this all up in order to measure times T1 and T2. Let's do at first the T2. So at first, I'm giving it the pi pulse. So we have at first the spins precessing along the z-axis. The only component of the magnetization that is constant over time is the z component. Now comes the pi pulse. I'm flipping them. And now I will get the signal coupled into my coil along the y-axis. But what happens is I have this dephasing process going on. So this magnetization, the net magnetization, will get weaker and weaker. They will, some will stay back in terms of phase, some will go ahead. So this is shown in an animation coming on the next slide. So I'm telling you what's happening, and then when you see it, I think you will understand better what I mean. So they will dephase and open up, and then after some time that you choose, you send a pi pulse, which means that now you are rotating the magnetic dipole 180 degrees. And then, because of the phase relation, everything will come back and will at some point again have a perfect overlap or coherence in terms of vector position. And then what you get as a signal is an echo of the original magnetization you had right when you flipped it into the XY plane. Let me show you what I'm talking about. Okay, so 90-degree pulse, we flip it into the XYZ, and the 180-degree pulse, and then comes the echo. Okay, this is a little fast. Maybe I can stop it. Okay, I'll just talk about it while it's actually going on. So we come in with the 90-degree pulse that flips it into the XY plane. Then it folds up because you have this dephasing. But the dephasing that happens is something that you invert by sending a 180-degree pulse, because then everything will take, with the same dephasing, will go back to its original state, and they will arrange in a phase matching condition after the time t and produce an echo. So this way you can eliminate all these dephasing effects that appear due to field inhomogeneities and other problems that occur in a setup. And the only thing that you cannot compensate through this process is the fact that the spins have this energy loss and this kind of relaxation process through the coupling between each other. So when you compare now the pulse or the strength of the signal you had right after the 90 degrees pulse with the pulse height of the echo, you see that the echo is like all echoes. So if you scream into a cave or so, it doesn't have the same intensity as what you send out because of loss. And so from this difference in height between the actual pulse and the echo of the pulse, you can derive T2, because this is the direct loss of the direct loss of your face locking. And now let's go back. It's best said like I've said here. So it is the decay constant for the coherence of the transversional part of the spin magnetization due to this coupling between the two spins. And with this process of doing the 90 degrees flip, and then after some time that you choose flipping back 180, you create these echoes, and the difference of the height echo to the original pulse is exactly measuring this loss that you have, and from this you can derive your relaxation time in principle, right? So this is the T2 measurement. You do the measurement in time domain and you convert this back through a Fourier transform into frequency space. Then you have again your peak where you have the resonance for this flip from here to there with the width determined or in relation to your relaxation times. This is now T2. So this was the transversal part. And now what we still have to cover is the T1 measurement. So
maybe before we go to that, could you go back the slide before? I do not really see it because I thought the echo would be exactly of the same. To what do we compare it? To the one before? So we have these two stages where we have the flip first, and then at this point it is exactly in phase. And we compare this intensity to the echo after it then.
We compare, so I see this dashed red line. This should show some very, very slowly decreasing height of the pulses that you create through this echo trick. So it's basically in this picture, only the energy or the height difference between your peak at 90, so the 90 degree pulse, and the echo after. This is what you compare, and there's something lost because in the moment, at first you have you are in a state where magnetization looks like this, the net magnetization, right? So all the spins are precessing, but in ensemble average M looks like this. Then comes the 90 degrees pulse, and it gets this well-defined magnetization into the XY plane. And now this magnetization vector is precessing because it's still precessing in the Z field. And whenever M passes your coil, you get the signal into your detector, right? So you can measure the precession frequency with a certain strength, right? Because this depends on how many of your spins in this sample that you have are aligned so that you get the signal. And this alignment itself, after placing it into this rotational phase in the XY plane, this will get weaker over time. Okay, and this weakening boils down to a difference in the signal strength between the first peak and the echo after, if you repeat this again by an 180 degrees pulse, so you get you can watch how the pulse height decreases. You make an exponential fit and derive your relaxation time directly from this fit, basically.
Can I also ask a question about this?
Mm-hmm.
The dephasing mechanisms, are they constant for each specific spin? Because at first I would have imagined that these mechanisms that lead to different rotational velocities of the different spins, they would occur randomly. But now it seems to me that any spin rotating slowly will rotate slowly throughout, and any spin rotating quickly rotates quickly all the time. Is that correct?
So the T1 and the 2 times, they are specific actually for which type of nucleus, obviously, you're looking at and how this nucleus is placed in a molecule. So depending on the environment, so we hit we are aiming, for example, for protons. That makes the most sense because in organic chemistry, we have the H atom in many types of different bonds and constellations set up in these structures of the tissue. And so this will give you different values for T1 and for T2. So both of these values are specific to the molecule or to the type of tissue you're looking at. And so what you can see in a sample is that you have several different resonance lines with different T1 and T2 times. And what the computer has to do is to learn and identify which type of molecule it is based on the relaxation times it measures, T1 and T2, because it measures all of them basically like when you swap through frequency, you measure all of these lines and obtain a whole spectrum, which can be more or less complicated depending on the type of molecule that you have in your system. But we will get to this link to the actual type of tissue on the next few slides. So this is just the measurement T1. I have to cover also the T2. I also have to cover the T1 measurement. As I said, I mean, you can simply just do this excitation from the ground state to the excited state, and then look at the width of your peak in frequency space, because this shape is related to the relaxation times, but it's also more accurate and the standard to do this with pulsed spin and echo measurements in the time domain. And this is a very fancy way of how it is done. Look at this. You start again with the magnetization in the ground state, so everything is aligned, for example, with magnetization pointing upwards. And now you come again in with an excitation through a B field along the x-axis. So our magnetization in this B field, our magnetic dipoles will have to make a precession movement now around the x-axis, as it's shown here. And I'm choosing a duration for the excitation so that we get an angle of 180 degrees. So this is why it's called a pi pulse. We start now with a pi pulse, meaning we are pumping all the from the ground to the excited states in this energy picture, from the lower to the upper state. And then what you do is the following: to have more sensitivity in measuring what's really going on, you measure along the y-axis with the coil. You put the coil there and you're waiting for a signal according to the precession frequency. Now, in the state you started from, you have no net component in the xy plane, so there is no signal. Also, in the excited state, when flipping it down, you don't have this. But what you can do is, you flip it, so you do the pi pulse and you are in the excited state, and then there will have this relaxation processes will take place. And what you do is you wait a certain time, and then you flip what is left of your magnetization, your longitudinal magnetization, you flip it into the xy plane through a pi half pulse. And then all of a sudden you again see signal in your coil along the y direction, because you flipped it into the xy axis where your coil is sitting, and you get the signal. Now the signal strength will depend on how much of your magnetization was actually left when you did the flipping. So what the computer setup is then doing is the following: it makes the pi pulse, and then it waits a certain time and makes the pi half pulse, and you measure the signal. It waits till everything is relaxed. It again does the pi pulse, waits a little longer, and does the flip again, and looks what's left of the magnetization. What do I see when coupling in at the y-axis? And it repeats this till it reaches the point where I've waited exactly the time where the magnetization is going through zero. From going from here to here, because it's relaxing. At some point it will have zero, so the projection onto the xy axis is giving you a zero. And so if you repeat and scan over different times, so you repeat this pi half pulse at some time, then a little bit later, then a little bit later, you get this type of signal. At first, if you do it right after you did the pi pulse, you will have maximum intensity in your XY plane because there was no time for relaxation, right? But if you wait a little longer, there will be less of magnetization, net magnetization, which stays and which is projected onto the XY plane, and then less and less. And at some point, you will go through the zero position. And if you continue, you will get the opposite signal, obviously, because you're already back to the original magnetization direction. And from this change, or from this line, you can derive the T1 time. So you can basically, through this repeated measurement for different times, you can conveniently measure your T1 time. So this is something where you get a lot of accuracy because you can repeat this measurements like millions of times because these are so short processes, right? So you can repeat this many times to get a good measurement for T1 through this measurement or T2 through the other measurement. So in this pulsed approach, you either do the pi half followed by the pi to do the T2 measurement, or you do the pi followed by the pi half measurement to get the T1 thing through this setup as I described. So this is how it's typically done in automatized NMR machines. And so we end up with these times T1 and T2, which we can use then to get information or translate this into certain features. One of them is the actual. So let's put it this way. In the end, we have three ingredients or three handles that tell us something about the piece of matter in our sample holder. We have the actual resonance frequency, and we have these times T1 and T2. So how does this now translate into useful information? Well, if you look at a certain spin, for example, you are looking at the proton, so H1, or for example, carbon-13, they have a certain typical resonance frequency where they would adsorb, which is the flipping of the spin from here to there if there was no environment. But then each of these nuclear spins is embedded in this atom, right? And is surrounded by an electron hull. So this means, because the electron is a flexible, is a charge distribution, it has this shielding effect, right? So it has it reacts as a diamagnetic and compensates part of the magnetic field that is applied externally. Right, so because you have the electron distribution around the nucleus and you have some shielding of the magnetic field because it will arrange as a diamagnetic compound in a way to compensate some aspect of or some parts of the B field. Therefore, depending on your actual environment, so is this is this hydrogen, is this nucleus, this proton, is it attached to a C? Is it attached to an O? Is there a double bond somewhere in nearby, and so on? So this will all play a certain role for this so-called shielding constant. And then there will be this interaction with neighboring nuclear spins. It's only these spins that are communicating each other because they are in the same energy regime that we are using to excite them, right? So there's a coupling of the spins between themselves, and this comes in as this J coupling. So we have the environment or shielding constant, which causes a certain chemical shift, means that it shifts the resonance frequency a little bit, and then you have a certain splitting because of the coupling between spins. And here I have taken one example from Wikipedia, hexaborane B6H10. And so it is something that I tend to ask at examination sometimes, if you look at the two spectra, you can see one which is in the range of 40 megahertz and the other one around 2.8 megahertz, and you can see some structure. And the chemical shift is due to different positions of the same type of nucleus in a given molecule, for example, right? And so what would be your guess for the different scenarios? Which spectrum belongs to which one? So you would have to look at the molecule as it's shown on the right-hand side. You can see it's boron and hydrogen in some site setup. And then the more complicated spectrum will belong to the atom which has the more complicated or has a more variation in its actual appearance. So what are the possible environments you can find the boron atom, and what are the possible environments you can find the hydrogen atom in? And which one is more complicated, or which one of them has more environments?
I would guess the hydrogen atom is the simpler one because it can only be attached either to one boron or to two. And so I would say maybe the right-hand one is the hydrogen, and then the boron. Boron can be. Sorry. Yeah.
So your argument is perfectly correct. So you say with environments, and then that is the right way. But you sort of did the wrong analysis in terms of how many environments you can find. Because look at the boron first. How can boron be arranged in this molecule?
Oh, right, yeah. It can either be attached to the 1, 2, 3, 4, 5 other borons, and the hydrogen on top, or the other boron is the second.
Right.
The one that has two hydrogens and two borons. Yeah.
Yes. So you only have two situations for the boron. One is called this is the apex position in the pyramid on top here, and the other one is boron here, and here. This is all the same position. So you only have two different environments for the boron. But if you look at the hydrogen, it can be bonded to a boron at the base of this pyramidal structure. It can be as a double bond, as a connection between two borons at the base, and it can also appear as the hydrogen directly at the apex atom in the center here at the top of the pyramid. So in this case, for hydrogen, we have more environments, so this will give a slightly more complicated spectrum. And also the proximity of the hydrogens in comparison to the proximity of the boron atoms tells you that the J coupling must also be stronger, and therefore, see, this is what causes the J coupling here. Here, A, these are atoms, hydrogen atoms of one type, B would be hydrogen atoms of the other type, and then C, the third one. So this is the hydrogen one because we have more environments. We have three environments, and we have a wider effect of the J coupling. So this is just one example. You can see that for a chemical compound, when putting it into an NMR setup, you get different spectra, and you can derive from the spectra what type of environment you find this nucleus in, and from this you can derive also structural information. Another thing is that the amount of how often an atom is typically found in a certain configuration is directly coded into the intensity of the spectrum that you can see here, right? Because I mean, for the boron case, it is very obvious. So we have 1, 2, 3, 4, 5 boron atoms that are in this environment type 1, and only one in this environment type 2 here at the apex. So this is the 5-to-1 ratio that you can see in this and in this group, right? So you can derive something, information on structure of a molecule in a compound. So you can use it for chemistry in a lab to just classify and study structure of, for example, organic molecules. Here, this is very versatile because we're doing it at the hydrogen and at the boron. In a other setup, like in a medical setup, you will just go for one type of atom, for example, for the proton, and look at the possible environments. And there are books and tables where you can see what is the typical shift of a proton in this environment or in this functional group and so on. So with this knowledge, you can really build or can derive what type of tissue or what type of molecule that's in your sample. And the last thing,
maybe,
Yeah.
sorry. No, maybe let's ask this at the end.
Mhm.
You can go.
Okay.
I will ask it.
then I wanted this to be shorter. Actually, because I had the time, I was just using it, I guess. But it's just a few slides left. So one thing that we still need to link it to is the fact that in nuclear magnetic resonance applications in medicine, we would like to do some imaging. That means we also need to know where our probe is sitting or where a certain adsorption or where a certain type of material or molecule is found. And what would be the easiest way to also have information on the position in space? What's your guess? How are we getting there? So right now we only have different resonance for different types of environments of these protons in tissue. But if I want to also know about their actual position somewhere in space, what could I do?
Maybe have more sensors that are spatially apart.
So that would probably be an option if you have something that is adsorbing and different distances to the sensor would reduce the signal strength, but that is not so accurate, I guess, and would introduce a couple of other problems in detection. Think of it this way. What is actually influencing the actual resonance frequency?
Make the field inhomogeneous.
Exactly. Yeah. The field itself is the factor that determines the actual splitting and therefore the resonance. So if you have an inhomogeneous field, then and you know the field strength at each position in space because it's a well-defined setup, then you know which resonance to expect where in space. And therefore you can identify based on this knowledge where this type of resonance must be. So if you say, okay, this is an H atom attached to a carbon in a single CH bond, then it also depends now on where this resonance is measured with respect to the position in the field, because there is different field, therefore different energy splitting, and therefore a certain resonance shift. And with this additional knowledge through the inhomogeneous field, you can get a spatially resolved picture of your structure of your material. So if you say, okay, this type of CH or this type of proton is typical for fat tissue, or this type of proton environment is typical for bone structure or for skin or whatever, then you can identify whole parts of your sample as some type of tissue with respect to position in space. And so this is how you create then the three-dimensional imaging, from magnetic resonance applications in the medical sciences. Okay, since I'm really out of time, just quickly, one other thing that is basically the same thing. It's just not about nuclei, but electrons. There are cases where you have molecules that do not have the nuclear spin, but they have an unpaired electron spin. And in this case, you can simply do exactly all the things that we just did here for the nuclei, also do directly with the electron spin. So you have an unsaturated electron spin, 1/2, has two possibilities of how it can be arranged in a magnetic field. And therefore, you can also do the same procedures with the flipping as we discussed before. However, since the Zeeman splitting is much, much larger here, because the magneton, so what's connecting the angular momentum to the dipole moment, is much larger for the electron in comparison to for the nuclear spin, you get much larger energy splittings. And so before we've been in the megahertz to gigahertz regime, so you can easily remember, as people of Graz, a typical frequency for the proton is around 100 megahertz. So like FM4 here in Graz, this is the resonance frequency for excitation of the nuclear spin of the proton. And in the ESR spectroscopy, so if it's about the spin of the electron, it's about 2,000 times larger splitting, and therefore the energy splittings are in the range of microwaves. Therefore, I think we have a setup exactly here at the Institute of Experimental Physics, one floor above my office here. There is an old ESR machine, and since it's operating in the microwave range, it has these waveguide setups to couple in the necessary power for microwave excitation. And the B field is something you can still handle without wasting too much money, because you only need B field strength in the range of a couple of about 1 Tesla, whereas in a medical setup you definitely need this specially cooled superconducting coils, because you are in a range where you have to 10 to 20 Tesla. Okay, right, so this is just an energy comparison. On the left hand side, NMR in megahertz, and EPR, the electron spin resonance or electroparamagnetic resonance, in the range of gigahertz. I'm not so fully happy with this graphics from Hertel and Schulz, because it's boiling two things into one. It's actually two graphics, one diagram for NMR and one for EPR. You can just, if you rescale them and push them together, you can show the same type of dependence with respect to field strength, because it's a linear dependence. The stronger the field, the more the splitting. You can bring it together into one picture. However, in the NMR case, it is the MI, so the nuclear spin, for example, 1/2 minus 1/2, or in the EPR or ESR case, it is the electron spin with MS plus minus 1/2. Okay, and with this, this is all just some setups, not so important. You can read this up and find some details in Hertel Schulz if you're interested, but I won't go into this right now, and rather come to the recap questions. So if you please grab your phones quickly and use the session code PXCMA. We can cover 3 questions. They should be online right now. I read it to you. Question number 1. Nuclear spin is 1/2. Total angular momentum is 3/2. How many F states are possible? Possible questions are possible answers 2, 3, or 4. Question number 2. How can T2 be determined in NMR from the echo pulse? Is it the time delay between pi pulse and echo? Is it the decay of the pulse intensities, so the height of the pulses? Or is it the time delay between the pi-half pulse and the pi pulse? And question number 3. Why are EPR, so electron paramagnetic resonance measurements, in the gigahertz regime and NMR in the megahertz regime? A, resolution is more important in NMR. B, because the nuclear magneton is much larger than the Bohr magneton. Or C, the Bohr magneton is much larger than the nuclear magneton. And D, the Larmor precession of the electron is much faster than the nuclear spin. So these are the possibilities. Okay, I'll wait for a few more seconds. We have approximately, we have 14, 15, 12, so maybe a few more seconds to get the same numbers of votes also on the last one, which is a bit more tricky. Okay, let's see. Question number 1. Nuclear spin is 1/2, total angular momentum is 3/2. How many F states are possible? Total number. We have only 2. Why? Because it's relative positions, and if the nuclear spin is 1/2, it can be up or down with respect to the 3/2 position of the angular momentum. And this gives us 2 over 2 give 1, or 4/2, which is 2. So these are the 2 possible states for F. That was 2/3 got it right, which is okay. Then second question, how can we determine T2 in NMR? The correct answer is only one of them, from the decay of the pulse intensity, because the distances between the pulses is something that we determine in the setup itself, right? So because when I'm getting the pi pulse, when I'm sending the pi pulse, I'm turning it around, and at the same time it took between the pi half and the pi pulse is the time the next echo will appear. But the pulse height is the trick, because this is changing because of these losses. And finally, why are EPR measurements in the gigahertz regime and NMR in the megahertz regime? Here it was 2 correct answers, and most had the 2 questions identified. However, both of them are correct, and it's just 50% each. So maybe you didn't see that it's actually 2 correct answers. It's either the Bohr magneton being larger than the nuclear magneton. So this is one obvious explanation, because this is what connects the angular momentum to the dipole moment. And if it's larger, then you have a stronger coupling and therefore a larger energy splitting. But it's also correct to say this way: the Lamour precession of the electron is much faster in comparison to the Lamour precession you have for the nuclear spin, right? Because precession frequency translates directly into an energy, and therefore these 2 statements are equivalent. All right, okay, so I stop here and I stop with the recording, but you have time for questions. So let me stop here quickly.